I'd like to thank Laurent and the other organizers for bringing us all to this beautiful place and letting me speak. This is a little bit of a strange talk for me because this is building very much on recent work of Barmpalius and Louis Pye. So I mean, I feel like the big technical achievement I'm going to talk about is not mine. And what I'm going to give is a generalization, some observations, an application on that technical work that they did recently. So that's a little unusual for me. I'm not, and I'll try to make it clear what they did in a few slides. And the other thing I wanted to say about the talk before I started was that when I showed up in Wellington and as a postdoc and started learning about algorithmic randomness, I really thought that the whole left CE.real thing was done. This was all wrapped up in maybe the 2 years before I showed up. It was all being published, and I'll talk about some of that work. But I really thought that stuff was done and closed, and there really wasn't anything more to say that was kind of fundamental about left CE random reals. This talk is about me being wrong. But again, it was Barmpalius and Louis Pye who said something that I think is new and interesting, and I'll get to that. So first of all, what is a left CE real? I guess you probably all know. If you have a commutable non-decreasing sequence of rationals limiting to a real alpha, that alpha is left CE, and that sequence of rationals is called a left CE approximation. Now, the only reason I might even bother defining this in this audience is because these go by a lot of names. There are CE reals, left computable reals, lower semi-computable reals. I think left CE real is starting, well, I was going to say, I think left CE real is starting to become the standard term for them, except that yesterday we saw a talk where they were called sigma 1. So there's still a lot of names that they go by. Right CE reals are defined similarly, and it's easy to see that a real is computable if and only if it can be approximated from both directions. The Martin-Loff random left CE reals, and I'm not going to say Martin-Loff anymore. When I say random in this talk, I mean Martin-Loff random. The Martin-Loff random left CE reals are a particularly interesting class, and the key steps in understanding this class were made first by Chaitin and Solovay in '75. I mean, not independently, but separately. Kaludi, Hertling, Kusenov, and Wang, and Kucher and Slayman in 2001, well, published in 2001. And these were the results that I was saying. Basically, I felt like random left CE reals were just well understood, that was a closed subject. And altogether, these 4 papers show that alpha is a random left CE real if and only if it is the halting probability of a universal prefix-free machine. If and only if, and this is going to be a little more vague than the first 2, any left CE approximation to alpha converges at least as slowly as any left CE approximation to any other left CE real. Okay, I'll be more specific about that on the next slide. So the last of these conditions, like I said, was vague. It's often stated as saying that alpha is Solovay complete, but actually it's a lot stronger than just saying that it's Solovay complete, at least on the face of it, it's a lot stronger. It's equivalent, but, and I won't really talk about Solovay reducibility, so, except in passing, so I won't carefully define it. But I will be precise about that last of the 3 equivalent conditions. It's due to Kuchera and Slayman. It was a very nice result that basically wrapped these equivalent conditions up, proved that they were all equivalent. And they proved that if alpha and beta are left CE-reals with approximations alpha s and beta s, and beta is random, then there's a constant c such that alpha s is never closer to alpha than c times the distance between beta and beta s. So beta s is converging to beta slower up to a multiplicative constant than alpha s is converging to alpha. And like I said, this is actually stronger than saying that alpha is solidly reducible to beta. But since I'm not going to tell you what that means, this is the result that I want to talk about. Now, if we rearrange this, we just, division, alpha minus alpha s over beta minus beta s is less than c. And if alpha is also random, then in fact we have that there's a lower bound above 0 of alpha minus alpha s, and an upper bound below infinity of alpha minus alpha s over beta minus beta s, and an upper bound below infinity. That these terms are bounded above and below, away from 0 and infinity. And so this can be seen as saying that all random left CE-reals are essentially equally hard to approximate. That within constants, they converge the same way. Okay. Well, what Bronpalius and Lewis Pye did was say this kind of constant, within constant stuff is a lot better than that, actually. So what they looked at is the limit of alpha minus alpha s over beta minus beta s. And we'll call that, this is not what they called it, but we'll call it, because where we're going with this, we'll call it d alpha d beta. And so they looked at that limit. And what they showed was that that limit exists and is independent of the choice of approximations. That's a very nice generalization of, or I don't know, generalization is quite the right word, but it very nicely builds on the Kuchera-Slayman theorem. Because what it's saying is not only do all left CE-reals, random left CE-reals converge, essentially the same up to constants, asymptotically they converge exactly the same up to a single constant, and it doesn't matter what approximations you take. So that's very strong. And furthermore, because they weren't actually interested in this limit originally, they were interested in differences of left CE-reals. When are they random and when are they not? And what they showed is that d alpha d beta is 1 if and only if alpha minus beta is not random, is greater than 1 if and only if alpha minus beta is a random left CE-real, and it's less than 1 if and only if alpha minus beta is a right CE-real. And if you put this together with a little bit of linearity of limits, you get that d alpha d beta is equal to the supremum of the rational C such that alpha minus C beta is a left CE-real, and that's equal to the infimum of the rational C.
Left CE-real? You say left CE-real?
Well, it is a real, so calling it left C makes it a left CE-real.
But just being left C is not enough?
No. It is a real.
Oh, yes, sorry.
The context
not
is...
random. So you don't require randomness in the last...
no, randomness is free, actually. You could put random in there as well, and it would be fine as well.
Yeah,
sorry. I don't mean like a... left C is not ambiguous. Okay. And the infimum of the rational C such that alpha minus C beta is a right CE-real. And actually, this is what they proved. I've reversed everything because this is what I'm interested in, is the limit up the top. But what they actually proved was this, and kind of worked backwards up to here, showing that this limit exists. All right. So I think these are very nice results, and say something really new about left CE-reals and left CE-randoms. But I want to move these results from the context of left CE-reals to the context of DCereals because I think that's really the most natural context. And this shouldn't be shocking. I mean, they're interested in differences of left CE-reals. Maybe the right context is the DCereals. Because what are the DCereals? They're exactly the differences of left CE-reals. Now, Again, this goes by a lot of names. Sometimes these are called weakly computable. Downey Hirschfeld called them left DCE, which doesn't make any sense to me at all, but admitted that they should be called d-left CE, and Nice actually called them difference left CE. But all of those are kind of long. I'm just going to call them DCE and hope that that doesn't cause any real confusion. Or call them dcereals. I'll try to always say real and not just. So these go by a lot of names as well. Okay, and probably there are several more names as well. So if beta and gamma are left CE approximations, beta S and gamma S are left CE approximations of beta and gamma, respectively, then we could set alpha S equal to beta S minus gamma S. And then alpha S is an approximation of alpha in the sense that the limit is equal to alpha. And it's a nice approximation. The variation of the approximation is finite. And what I mean by variation is this thing, that the sum of alpha S plus 1 minus alpha S, the absolute values, is blah, 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 finite. So that's the variation, and the variation is finite. And it's just because the variation is bounded by the variation of beta plus the variation of gamma, but beta and gamma are left CE real, so their variations are just them. So, so basically we're looking at the approximation, we're saying how much does it move back and forth, what's the total amount that it moves, that's the variation. And this is actually, and we call such approximations DCE approximations. These are the approximations with finite variation, and these characterize the DCereals. And obviously, we've already done one direction. Every DCereal has a finite variation approximation. The other direction is pretty easy. And I wrote the proof, but here, every time your approximation moves in one direction, add it to one of the left CE-reals. Every time it moves in the other direction, add that to the other left CE-real. The difference is going to be the thing. That's what that says. See, every time alpha S plus 1 minus alpha S is positive, you add it to beta. Every time it's negative, you add it to gamma, and that's going to give you the representation of alpha as beta minus gamma. Okay. So those are the DCereals. They're clearly closed under addition, subtraction. That's without any thought at all. It isn't too hard to see that they're closed under multiplication, division. And in fact, they form a real closed field. All the roots that they should have, they do have. So any polynomial with DCE coefficients that has a real root has a DCE root. Okay, oh, and that's a result, that last one's a result, independently of Raichev and Ng. Okay, so now I want to generalize Barmpalius and Lewis's results to the DCereals. Because like I said, I think that's the natural context for them. So one thing that I want to do a little bit differently is I want to fix a benchmark. I want to fix a left CE real omega with left CE approximation omega S. And that's my benchmark to measure rates of convergence. And I'll define d alpha to be d alpha d omega, which was defined, before. But in this case, alpha, I'm taking a DCE real with a DCE approximation. So generalizing the context a little bit. And this isn't exactly just a translation. I mean, these results are, you have to be careful with, because you're dealing with DCE approximations and not left CE approximations. So you have to be a little bit careful with these. But it all follows without too much trouble from the work that Barmpalius and Lewis did. So the corresponding theorem is that if alpha is DCE real, then d alpha converges and it does not depend on the approximation of alpha. It's zero if d alpha is zero if and only if alpha is not random. It's positive if and only if it's a random left CE real. Negative if and only if it's a random right CE real. And you get the corresponding supremum and infimum characterizations of d alpha. Okay. So I do want to make a quick comparison between what d alpha tells us about DCereals and what the solid degrees tell us about left CE reals. The solid degrees, put all the random left c-reals in 1 degree. That's going to be the big difference. And the range of D on the DCereals puts all of the, sends all of the non-random DCereals to 0 and distinguishes the random ones. So in some sense, they're complementary. Now, a couple of observations about this. There is actually significant overlap in what the two approaches tell us about random left CE-reals. So one way to, one example of that is that Downey, Hirschfeld, and Nice, they showed, and actually it was I guess it was originally claimed in a paper of Demuth, and then they showed that the sum of any two non-random, yeah, sorry.
Sorry, I should question you. I'm too fast. So
sorry.
So random DCereals then when you apply, so there is you don't have a non-zero. You don't have a.
You want to say that
limit, non-zero limit on random. Random DCereals are always either left C or right C. Somehow it's not. It doesn't happen, but a random DCereal is neither left C or right C.
Yeah, actually, that's a result that, well, there it is. Redinger and Zeng proved that all random DCereals are either left C or right C. Maybe I should have put that comment first, because that's implicit in that picture that you see there. And I definitely did want to, and it's actually implicit in the theorem that I stated above. So I definitely did want to go into this. In fact, I want to show you the proof of this because it's very simple. But that'll be in a couple slides. So, okay. Okay, so that's a good observation. Back to the significant overlap, Downey, Hirschfeld, Nice showed that if you take that the sum of two non-random left C-reals, and again I said this was actually claimed by Demuth, the sum of two non-random left C-reals is non-random. And that was important in the Solvay degrees because it showed that this top degree doesn't split because sum turns out to be joined in the Solvay degrees. On the other hand, it plays a nice, it easily follows from basic properties of this D operator. It's going to turn out to be linear, and so maybe I should just write this. I don't know if I can. Is there chalk? Oh, there's plenty of chalk. So it'll turn out that D alpha plus beta is, and this is just basic properties of limits, D alpha plus d beta. And so if this is non-random, this is 0. If alpha is non-random, this is 0. If beta is non-random, this is 0. So you'd get 0 plus 0 equals 0, which means that alpha plus beta is non-random. So it fits very nicely into the context of this operator on DCereals as well. So there is overlap in what the two approaches tell us, or at least what's interesting in both approaches. And I'll talk more about that as well. Another thing that Redinger and Zeng did, which would bring these two pictures closer together, because another difference between these two pictures is that this is about left C-reals and this is about DCereals. They pointed out that if you make a slight change to solvay reducibility, then it is actually meaningful in the DCereals, and the top degree still contains all the randoms. So that work I don't think is very well known, and so I didn't want to draw this, I didn't want to write this picture up in terms of DCereals because I think that would have been confusing for the people who are familiar with solvay reducibility more than clarifying. But that seems to be a nice extension to the DCereals and would make this comparison a little bit more clear.
Sorry, so who are they? So Redinger and Zeng?
Yeah, yeah. So, sorry, say, yeah. All right. Now, another observation is that, and this is implicit in the title of the talk and the notation that I chose. I mean, this should not be a surprise. I've been leading up to this, is that D acts somewhat like differentiation. Well, there's other reasons it shouldn't be a surprise, actually. It shouldn't be a surprise because it was defined as the limit of a difference quotient. I don't know how many of you teach calculus like every year, but there's some things like you just don't miss after a while. And it's meant to capture a rate of convergence. It's like, this is, yeah, okay. It's not surprising that it acts like differentiation. And in fact, it is a derivation on the field of DCereals. I've already mentioned this right there, and that was actually known by, that was known by Paulius and Lewis Pye. They used that. And it also satisfies the Leibniz law, and again, if you teach calculus, you just write it down, it's totally easy. Same proof as usual. However, it does not make the DCereals into a differential field because it maps outside of the DCereals, unfortunately. So it doesn't make them a differential field. It is a derivation, and we'll get some by the end of the talk, a nice application of the fact that you have this derivation on the DCereals. But for now, let me just point out that the range contains at least all delta 2 reals. In fact, I'm sure it's bigger than that, but I don't know what the range is. I have some ideas. It'd be nice if it were the zero jump left CE-reals. That would be nice. It'd be actually even kind of cooler if it were the non-random zero jump left CE-reals. But anyway, I don't know what it is. And I know that it's bigger than the left CE-reals, or the DCereals. Okay, but another observation, another way in which D acts like differentiation, is that if you have a computable function on a DCereal alpha that's differentiable on the real, then F alpha is a DCereal, and dF alpha is F prime alpha d alpha. The second part is, again, just play with limits is totally easy. The first part is, well, assuming that all the limits exist is totally easy. The first part, you need to know that one of the limits exists. And it's actually not hard, but when I originally wrote this down, I was assuming that F was locally Lipschitz or something like that, and then I realized, like, oh, no. You can just get it by assuming that F prime of alpha exists. You can come up with a DCE approximation of F alpha. So, but it is pretty easy. What it allows us to do is apply basic identities from calculus. So d alpha n is n alpha to the n minus 1, d alpha. d e to the alpha is e to the alpha d alpha. Since d omega is 1, d e to the omega is e to the omega. When I saw this stuff, I thought this is really, really cool. And for a little while, I thought this was the direction where things were going to happen. And, but then I realized because the range maps outside of the DCereals, you can't really talk about second derivatives, third derivatives, and so on. So you can't, I was hoping that you could develop some kind of a Taylor theory, that sort of stuff, and maybe even get, canonical forms for left CE-reals or something like that. That would be great, but nope. I don't think that this is a direction that goes, it's cute, but I don't think this goes anywhere. Although I think we will we'll apply this at some point later on. But I think it doesn't go anywhere because you can't really develop all of calculus when you have a derivation that maps outside of your field. It really is really kind of limiting in some senses. Okay. So now, are there any questions about the results that I listed? Because now I want to give some, let's call them proofs of these results.
Sorry.
Yeah.
You first fix the omega, so the value of d does not depend on
Choice of approximation.
choice of omega.
No, it totally depends on the choice of omega. I mean, and all of, like whenever I write d alpha down, or d anything, like that fixed omega matters. If I change omega, it's going to scale everything. The approximation to omega doesn't turn out to matter, of course, but the choice of omega matters. If I replace omega with 2 omega, then I've just halved all of my d alpha for all alphas, right? So that choice of omega does matter, but I think it's just easiest to fix this benchmark and then forget about it. Does that make sense?
Yeah.
Okay.
But concerning this point, if you change omega, wouldn't you expect something like a chain rule?
Oh yeah, absolutely. But again, this is just very simple, a very simple limit observation that basically that yeah, like d alpha d beta is equal to d alpha d omega over d alpha, d beta d omega. I mean, everything, all these limits exist, assuming that beta is random. All these limits exist, and then, and so, yeah, you can use a chain rule to exactly the way you would want. Yeah. Yeah?
So I think when George was telling me this, I was going through my head that if you think about solid reducibility, it essentially says that so gamma is less than, if alpha is less than beta, then alpha is c times beta plus gamma.
But that's C actually, no, that's C actually to, oh. Yeah, no, that fits nicely into this stuff as well.
But then if you think about the limits, provided you can prove that the non-random bit goes to 0, the gamma bit, then it's clear that there's got to be a limit because it's basically c times beta over beta. And I can't take that limit because that's c. That's why I was wondering.
No. I think, okay, for one thing, why are you saying that the gamma is non-random?
That's a good point.
Because it doesn't have to be in general.
It doesn't have to be.
Okay. No, let's talk about this after. If you think that there's an easier way to do this, because actually, I mean, I'll sketch the proof of this, and it would be nice.
Not this video, but I'll talk about it.
Yeah. Okay. Okay. Now I'm gonna sketch. This is really the sketchiest proof I'm going to give. That the limit of alpha minus alpha s over beta minus beta s converges. And this is not their proof because, like I said, they didn't prove this directly. I'm reversing everything. So this isn't really their proof. And I don't know how it compares to their proofs because I don't read. But you can, if anyone wants to read, and tell me, that would be nice. Anyway, this is the sketchiest proof I'm going to give, but I will tell you exactly where you have to do a little bit of work, and the work isn't that bad. So assume for a contradiction that the limit diverges. By Kucheres-Slayman, it's not that bad. The lim sup is bounded below infinity, and on the other hand, all the terms in the sequence are non-negative, so the lim inf is bounded above negative infinity, in fact, by 0. And so you know that there must be a rational c less than d between the lim inf and lim sup, assuming that the limit doesn't exist. Right? I mean, this is true as long as this doesn't go to negative infinity and this doesn't go to, and this doesn't go to infinity. Right? So anyway. In particular, there are infinitely many s, and this is just by rearranging, doing some multiplication. There's infinitely many s such that alpha s minus d beta s is less than alpha minus d beta. That uses this inequality. And infinitely many t such that alpha t minus c beta t is greater than alpha minus c beta. That uses this inequality. Okay, so I just repeated that statement. And if you could take such s and t, then with a little bit of algebra, you could figure out that beta, and I'm not going to go through this algebra, but it's just algebra. I don't mean algebra in the deep sense. I mean algebra in the shallowest possible sense, moving things around. You can see that beta is less than this, not as monstrous expression as it at first looks. Alpha t minus alpha s plus d beta s minus c beta t over d minus c. This expression converges to beta. These cancel the limit. And you just get d beta minus c beta over d minus c, so it converges to beta. So we have these upper approximations to beta. As long as we can find s and t satisfying these inequalities. And now beta is a left c-real, so we have lower approximations. Having upper approximations that converge to it is a good thing. If we could do that effectively, we could compute beta. Beta would be left CE and right CE. Well, we can't do it computably, but we can do it well enough to cover beta with a solivate test. And the difficulty, as I said, is that you cannot effectively determine s and t that give you these properties. But if you see an s such that alpha s minus d beta s is particularly small, you think, that might be a candidate. Or and then later on you see a smaller one, you go, well, that's a better candidate. You see a t such that alpha t minus c beta t is particularly big, you go, that looks like a good candidate. You see later on a bigger one, you go, that's a better candidate. And you try to match up the good candidates. And then that takes a little bit of guessing and updating dynamically. And then you have to be careful that you don't add too much to your Solovay test that you're building. So when you add something to your Solovay test and then you update your guess about t, you say, well, I'm not going to add a whole new thing to my Solovay test. I'm just going to extend the one that was there. And then there's about a page showing that that works. And that's the part that I'm not going to do. But it's not super hard. It's just fiddly. And the whole point, if you get anything out of this, is that you can get these upper bounds for beta, and you can get them effectively enough to cover beta with a Solovay test. OK. Now let's talk about DCereals. And now I'm actually going to talk about this result that you pointed out of Redinger and Zeng, that all random DCereals are either left CE or right CE. So they made an observation that if you take a DCE approximation of alpha and consider the Solovay test, where you just, for every time alpha increases, you put alpha s, the interval from alpha s to alpha s plus 1 into the Solovay test. This obviously has finite weight because the approximation has finite variation. And if alpha s crosses over alpha infinitely many times, then alpha would be covered by this test and would be non-random. So we have three possibilities. Either alpha is always to the left, almost always to the left. Alpha s is almost always to the left of alpha. Alpha s is almost always to the right of alpha. Or alpha is non-random. Now, in case 1, fix a stage such that alpha s is always to the left of alpha. In that case, we can just take maxes, supremums, and get a left CE approximation of alpha. So alpha is a left CE real. In case 2, we get a right CE real. And in case 3, we get a non-random. So that's the proof that, are there any questions about that? I think this is a really sweet little proof. And totally, it was a surprising result when they pointed it out. So random DCereals are either left CE reals or right CE reals. And the observation has a converse, that if alpha is a non-random DCE real, then there's a DCE approximation of alpha that crosses over it infinitely often. And this isn't hard either. I needed this for technical reasons. This is not as exciting as the other one. You take any DCE approximation and any Solovay test covering alpha, and then basically every time you find yourself in an element of the Solovay test that hasn't been used, you go boom, 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 and tag the endpoint of the Solovay, of the interval in the Solovay test. You go just right. So what do I mean? We define a new approximation at stage S. We check to see if alpha s star is contained in an unused interval of the Solovay test. If so, mark that interval used and hit its endpoints with your new approximation. And otherwise, just stay where you are. And I'm doing this in multiples of 4 just to give myself room to do that kind of. Anyway. It's not hard to see that because the Solovay test covers alpha, that there's infinitely many intervals you'll use, and every time you use an interval, you cross over alpha. And every time you use an interval, how much more do you add to the variation of the approximation? Well, you cross over the whole interval twice. So you add twice the length of the interval. So the variation of the new approximation is equal to the variation is bounded by the variation of the old approximation plus 2 times the weight of the Solovay test. So it's still a finite variation approximation. OK, so this is a dumb little lemma. Now we're ready to actually get our hands dirty and do some of this work. If alpha is a DC real with approximation alpha s, I'm gonna before I prove that independence from the choice of approximation, I'm going to write this as d alpha s. Right? I'm not really allowed to write d alpha because you don't know that it's independent of the approximation. So I'll write d alpha s. Now it's really easy to see because limits have nice properties, like they're linear, that d alpha s plus beta s is d alpha s plus d beta s, and if c is irrational, then it works the way you think it should. This is assuming that, you know, this equality is true as long as any two of these converge, these limits converge. Right? Okay. Then the third one must converge and they're equal. Okay, so let's prove that d alpha s converges. Well, this is easy. This is super easy because we can break alpha. Alpha s is a DCE approximation, but we know how to go from a DCE approximation to a difference of left CE approximations. And so take the left CE approximations to beta s and gamma s such that alpha is equal to beta minus gamma. And then d alpha s is equal to d beta s minus d gamma s. But these exist by the main technical lemma, the really sketchy thing that I showed you previously. These exist. So d alpha s also converges. Okay. So that part follows from the convergence for left CE-reals. Okay. Now, if d alpha s is greater than 0, then alpha is a left CE-real, and the same for less than 0 and right CE-reals. Well, okay, so if d alpha s is greater than 0, then eventually alpha s is less than alpha, which means that alpha minus alpha s is positive. So all the terms in the limit are positive. Oh, no, wait. Have I gotten this? No, I'm going the wrong direction. Okay, let's try this again. If it's greater than 0, then eventually, right, then all the terms are positive, so eventually, if d alpha s is greater than 0, then eventually all the terms are positive. So alpha s is less than alpha. But remember, if alpha s is less than alpha past some point, we already have seen that that means that alpha is a left CE-real. Part 3 is similar. Okay, sorry. Proving the wrong direction. If alpha is equal to 0, then d alpha s is equal to 0. This really is embarrassing, but this has to be proved for the next part. And is proved by a little bit of trickery. So assume that alpha is equal to 0, but we have some weird approximation where the limit is non-zero. Well, pick an integer c such that 1 plus c times d alpha s is less than 0. C can be positive or negative. So d omega s plus c alpha s is less than 0. But that means that omega is a right CE-real because this is an approximation. This is a DCE approximation of omega plus c times alpha. Alpha is 0, so that's just omega. So we have a DCE approximation of omega proving that it's a right CE-real. And that would make omega computable, which is a contradiction. That's a bit of silliness. So now if we have any two DCE approximations of alpha, then d alpha s and d alpha s star are equal, and all you have to do is take the difference of these two approximations, and that gives you a DCE approximation of 0. So it has to be, so d alpha s minus alpha s star has to be 0, and we get equality. Okay, so here's the things that I just proved. If alpha is a DCE approximation of alpha s, then d alpha s converges. D alpha s is greater than 0 implies that alpha is a right CE-real. Less than 0, left CE-real, greater than, less than 0 is right CE-real. Equal to, if alpha is equal to 0, then d alpha s is equal to 0. Oh, you can read. Okay, this is what we just proved. I just wanted to put it all in one slide. So we're really ready to recover the work of Barmpalius and Louis Pye, generalized to the DCereals. And obviously we've already shown that now if alpha is a DCereal, then d alpha converges and does not depend on the approximation of alpha. That's really key. We have a thing we're now talking about. D alpha is a well-defined thing. And that's immediate from the lemma, the first and last part of the lemma. D alpha is equal to 0 if and only if alpha is non-random. It's greater than 0 if alpha is a random left CE-real, less than 0 if alpha is a random right CE-real. Okay. I'm just restating all the properties from earlier. So if alpha is not random, then it has an approximation. This was the dumb lemma that I proved. It has an approximation that crosses over infinitely often. Well, that means infinitely often alpha minus alpha s is going to be positive, and infinitely often alpha minus alpha s is going to be negative. So if you look at alpha minus alpha s over beta minus beta s, those terms are infinitely often positive, infinitely often negative, and yet they converge. There's only one thing that they can converge to under those circumstances. 0. On the other hand, if alpha is random, then it must either be a left c.e.real or a right c.e.real. We also proved that. So assume that alpha is a random left c.e.real. By Kuchera-Slayman, there is a c such that, well, this holds, which means that d alpha is greater than 1 over c. Just dividing out. So d alpha is greater than 1 over c, which means it's greater than 0. So all the terms are greater than 1 over c. So if it's a left c.e.real, then if alpha is a left c.e.real, then d alpha is positive. If alpha is a right c.e.real, then d alpha is negative. This proves that d alpha is equal to 0 if and only if alpha is not random. And it proves one direction of each of these, the if direction. That if it's a left c.e.real, then if it's a random left c.e.real, then d alpha is positive. If it's a random right c.e.real, then d alpha is negative. But the other direction follows because, for example, if d alpha is greater than 0, then it's random by 2, and left c.e. by the previous lemma. So it's all there. It's all there. It's all done. And we proved all of this except, well, the last little bit. But the last little bit just follows from linearity. From the fact that d of alpha minus c omega is d alpha minus c, and then you can just work it out using the things above. So that gives us all of the basic properties, and I've already pointed this out on the board over here, but we don't lose anything by working with omega as a fixed benchmark because if beta is random, then d alpha d beta is just what I've been calling d alpha, divided by what I've been calling d beta. But it would have been hard to write this because I would have written d alpha d beta is equal to d alpha d beta, and that would have been d alpha divided by d beta. That would have been confusing, so I'm writing it out here. But there's no ambiguity is what I'm saying. Okay, so we lose nothing by working with this fixed benchmark, and I think we gain a certain kind of clarity to these results. Okay, so I'm done with giving sketchy proofs, and if you were falling asleep, then you should, come back because I want to talk about something very. I'm going to apply now this work, but I'm not going to get my hands so dirty with these proofs. The proofs that I skipped, like the Leibniz property and such, are really easy. So I want to talk about the field of non-random DCereals. If D is the derivation on a field, is always going to be the case that its kernel, in other words, the things that it maps to 0, also form a field. In this case, that means the non-random DCereals form a field. Moreover, another general fact, though I could not find this anywhere, but it's just a general fact, it's not hard. If the underlying field is a real closed field, then so is the field of constants. So the non-random DCereals are a real closed field. Now I'm actually going to sketch this proof because I think it's nice. And I'm going to do it in not the general setting. I'm just going to prove that the non-random DCereals are a real closed field, but the proof is general. So first of all, if alpha and beta are non-random DCereals, then their sum is non-random because of linearity. Because d alpha plus beta is d alpha plus d beta is equal to 0, so alpha plus beta is non-random. It's easy to check that alpha minus beta, alpha times beta, and alpha divided by beta are also non-random. So the non-random DCereals form a field, and it's just a little bit of manipulation of this derivation that we have. Now, let's take a polynomial whose coefficients are non-random DCereals and take alpha to be a root of that polynomial. The DCereals form a real closed field, so alpha must be a DCereal, and all we have to do is show that it's non-random. That's all we have to do. So we may assume that alpha has multiplicity 1. as a root, just by the standard trick that if it doesn't, we take the greatest common divisor of p of x and p prime of x. That also has coefficients in the field of non-random DCereals, because greatest common divisor only requires field operations, not magic. So it ensures that p prime of alpha is not equal to 0. Assuming that, I mean, what ensures, in other words, if alpha has multiplicity 1, then p prime of alpha is not equal to 0. So this is standard. So I claim that d p alpha is equal to p prime alpha d alpha. And this, by the way, this doesn't follow from the earlier stated result for computable functions, because p here is not a computable function. It has non-random DCE coefficients, right? But it follows by an easy induction on the derivation properties. You're just applying the derivation properties to a polynomial. It's easy to see that, and the constants behave like constants. They have derivative 0. So the non-random, so it's an easy induction. And rearranging, we get that d alpha is equal to dp alpha over p prime of alpha. But p prime of alpha is non-zero, and p alpha is actually 0. So we get d alpha is equal to 0. So alpha is non-random.
Also, the root is just a differential function of the coefficients, computable differential function. So probably follows also for this.
Sorry, say that again?
So if you have a root of a polynomial, the root is a function of coefficients, differential one, no? So it follows what you said before also.
I'm not sure to,
If the derivative is
I'm not
not zero,
sure.
then there is a way to reconstruct a differential way to reconstruct computable differential.
There's a computable function that takes the
root from the coefficients.
There's a, yeah, right. I didn't say that. I didn't say that for multivariate functions, but that should be true. That should totally be true. And you're right. You're right. That should be a different way to do it. Yeah, I think this way is actually a little easier. But no, that should absolutely work. You're right. So we approved that the non-random DCereals form a real closed field. And I should point out they were not even known to be closed under addition. But this was known. I guess I'll say that soon. This should be considered non-trivial. It's easy to prove the convergence of d alpha d beta from the fact that, that non-random DCereals are closed under addition. So this should be considered a non-trivial fact. The proof sketches, remember in my very, very sketchy proof, of the first of my sketchy proofs, the very sketchy one, I had these C's and D's between the lim inf and lim sup. Well, if you take those, you can see easily that alpha minus C beta is not random because C being here means that alpha S minus C beta S is infinitely often below it and infinitely often above it, given these two inequalities. And so the approximation goes, crosses over it infinitely often, so it's non-random. Same for alpha minus D beta. But if you take the difference, you get D minus C times beta, so that must be non-random if the difference of, well, if the sum of non-random DCereals is non-random, the difference of non-random DCereals is non-random. But this implies that beta is non-random, and that's a contradiction. So this was a very, very quick proof, and not very sketchy, from the fact that non-random DCereals are closed under addition of the main technical lemma. So somehow that closure under addition is interesting. In contrast, the non-random left cereals, I've already mentioned this, have long been known to be closed under addition. Like I said, claimed by Demuth and without a proof, but presumably I trust that if Demuth claimed it, he knew it. And independently proved by Downey, Hirschfeld, and Nice. So that leads us to a question, which is a very vague question. Why are the non-random DCereals apparently more difficult to deal with than non-random left cereals? I say apparently because, of course, it could be that somebody, maybe Rod has a very quick proof of all of this, and it'll turn out that really it was all pretty easy to deal with. We just were looking in the wrong direction. So, apparently, but I think there's a good argument in that you try to generalize this proof to DCereals, it's not going to work very nicely. And you get a strong consequence out of the fact that non-random DCereals are closed under addition. So there's an argument that that the fact is deeper for non-random DCereals. And I think I have an answer to this very vague question. So call a DCereal variation non-random if it has a DC approximation whose variation is non-random. Whose variation is non-random. Otherwise, call it variation random. And it's not too hard to see that the following are equivalent. Alpha is variation non-random if and only if alpha is a difference of non-random left CE-reals. Of course, you see where this is leading. There's a non-random DCE-real that is variation random. So it's a non-random DCE-real. Oh, this can be proved using a fairly simple finite injury argument. There's a non-random DCE-real that cannot be expressed as the difference of non-random left CE-reals. If you could express every non-random DCE-real as a difference of non-random left CE-reals, then generalizing would just have been easier. Okay, so this is a non-random DCereal that somehow still carries some kind of intrinsic randomness. It's hard to approximate without there being something random in that approximation. Furthermore, the real closure of the non-random left CE-reals is the field of variation non-random reals. As soon as you start taking differences of non-random left CE-reals, you have a real closed field. And so that's strictly smaller than the field of non-random DCereals. So the variation non-random reals are a real closed field. You can't easily get to all the non-random DCereals if just by starting with the non-random left CE-reals. Okay, so this is what I think is the reason why something more is going on with non-random DCereals, why the proofs for non-random DCereals are actually, in some sense, harder than the proofs for non-random left CE-reals. And that's it.